Hello everybody. I couldn't find a good video that covered all the material we need for section 5.3. So I decided to go over the notes myself, just like we would in class, and record it and put it out for you guys to watch. Go ahead and watch the whole video and then scroll down and answer the questions for your quiz so you can get the points for chapter 5 quiz. I'll go ahead and take my face off of it now, but you'll still be able to hear my voice and we'll go through the whole notes together. Section 5.3 talks about logarithmic functions and their graphs. We've got 5 objectives to cover: evaluate logarithms, evaluate common logarithms, evaluate natural logarithms, graph logarithms, and look at transformations. Let's go ahead and start with the first one. In order to evaluate logarithms, we need to look at the definition of a logarithm. This is one of the most important things in chapter 5. We will be coming back to this definition over and over again, so please make sure that you are very comfortable with this definition. And if not, go ahead and practice it until you do get very comfortable. The definition says that the logarithm is equal to an exponential. Y equals the log base b of x is the same as x equals b to the y. In other words, we're saying that y, which is the logarithm, is just an exponent. So logarithms are just exponents. All the exponent rules will apply to our logarithms, and the way to switch back and forth is with this definition. Notice that the base of my logarithm, because we read it log base b of x, is the same base as the exponential. The exponential b to the y equals x is the same thing as the logarithm. So this base b is the same for the log and the same base for the exponential. The exponent y is what the logarithm equals to, and the variable x is what the exponential equals. We will practicing changing back and forth from logarithms and exponentials more in this section. Things that you need to know about the logarithm is the fact that the domain is 0 to infinity for all logarithmic functions. The range is negative infinity to infinity for all logarithmic functions. And we could also rewrite our logarithmic as a function with f of x instead of the y. Notice that the domain and the range are exactly the same as the ones for our exponential equations. They're just backwards. Our exponentials had a domain that was negative infinity to infinity and a range that was 0 to infinity. The reason for that is because logarithms and exponentials are inverses of each other. Let's go ahead and practice switching back and forth from logarithms to exponentials. And this is how we will evaluate a logarithm. So we need to figure out what is the logarithm base 2 of 8 equal to. Again, in order to answer this question, to figure out what is y, we need to rewrite it with the definition. So I'm going to write down the base first. The base is 2. I'm going to write down the exponent. The exponent is always going to be whatever the logarithm equals to, so the exponent's y. And this is going to equal whatever we have in the inside. So 2 to the y equals 8. So this logarithmic question turns out to be an exponent question. What exponent do I need to raise 2 to get 8? Well, 2 times 2 times 2, which is 2 cubed, equals 8. So the exponent I'm looking for is 3, which means that my logarithm equals 3. Let's do the next one. The logarithm base of 5 of 1. So let's rewrite it. Let me write down my base, 5. They have the same base. My exponent is y, whatever the logarithm equals. And this exponential equals the inside of the logarithm. So this equals 1. So what exponent do I need to raise 5 to in order to get 1? Well, hopefully we know that any number to the 0 power is 1, which means that my logarithm must equal 0. And the last one, write down your base. 7 to what power equals 1 over 49? Well, let's rewrite 1 over 49 as an exponential base 7. Well, 49 is 7 squared, so this must be 1 over 7 squared. But if I want 7 to be the base, I can move it up to the top by using negative exponents. So 7 to the y equals 7 to the negative 2, which means that y is negative 2, so my logarithm must be negative 2. You can also calculate logarithms using your calculator, but I need you to be able to find them by hand with the use of the definition. So make sure you can use the definition and switch back and forth. Alright, let's talk about evaluating some common logarithms. The common logarithm is the logarithm base 10. As you can see from the previous examples, you can have a logarithm of any base. We saw 2, 5, 7, but really we could have whatever we wanted. However, in applications, the one that's the most common is base 10. That's why we call it the common logarithm. So if we have base 10, it's so common, and you know mathematicians are a little lazy. We like to not write down things. So it's so common we don't even write it down anymore. So if you have a logarithm base 10, you don't need to write down the base. Instead of writing logarithm base 10, we just write log x. If you just see the word log, you should know there's an invisible base 10 hiding in there. But it's a common logarithm, so we don't write it down. There's a few shortcuts we should remember from base 10. If you don't memorize them, you can always find them with your calculator, but it'd be nice to just remember a few of these. So if you have some time, make sure and go in there and take a look at these common ones and try and either memorize them or be really good with your calculator. All right, so let's find x. In the equation, log x equals 0.7482 to 4 decimal places. Again, because we just have the word log, there is no base, we should know that they're saying the log base 10 of x equals 0.7482. If I rewrite it with my definition, I'm going to have 10 to the 82 equals what number? Well, I can figure that out with my calculator. Hold on. Into our calculator, 10 to the 0.7482 is equal to 5.6001543, and so on. They do want us to round to 4 decimal places, so x must equal 5.6002. To be able to evaluate our logarithm, we needed to know it was base 10. So if it's not written, it should be base 10. Then use your definition to rewrite it, and then you can plug it into the calculator and evaluate. There is another one that is also very, very common. The common logarithm is base 10. The natural logarithm is base e. So let's go take a look at the natural logarithm. So if we have a base e logarithm, we call it a natural logarithm, and we would write it log base e just like we usually do. However, since this one is also a very important logarithm in applications, we use it a lot, log base e, so much that it has its own symbol. So the natural logarithm is the log base e, but we change it to just ln, natural log. That does look like in, but it is not in, this is ln, and it is a natural log base e of x, so natural log. And we also have a button for the natural log in our calculator. So this is our natural log. Oop, I pushed it a whole lot of times. Let's work with the natural log. Here are a couple examples. They want us to solve these equations. The first one says the natural log of x equals 1.335. Natural log of x equals 1.335. In order to solve that, we have to rewrite that. So we're saying e, because that's our base, e to the power, right? Our logarithm is always equal to the exponential, so this is my exponential. So e to the power 1.335 equals what number? And we are allowed to use our calculator to do that, so we just need to say e to the power 1.335 equals 3.7999. Well, that's going to be rounded 3.8000. So that means x equals 3.8000. For the next one, we have the natural log of x equals the log base 10 of 5.5. See, we're hiding, this is a hiding base e, and this is a hiding base 10. So to rewrite it with the definition, we're going to have e, again, this is my exponent, whatever the log equals is my exponent, so e to the log base 10 of 5.5 equals x. So to find x, I just have to put this in the calculator. So I'm going to say e to the log button is right on top of the natural log button, and you don't have to put base 10, it's already there with your calculator. So we just have to put in that, close that parentheses, and hit enter. So x equals 2.0967. So x equals 2.0967. Next objective is graph the logarithmic function. So there's a few things we need to know about the graph of our logarithms. Remember that they are the opposite, the inverse of the exponentials. So some of the things the exponentials had, we are going to take for the logarithms just in a little bit backwards way. So the first thing that we know is that the graph will always go through the point 0, 1. It also will always go through the point b, 1, where b is the base of the logarithm. The y-axis is always a vertical asymptote. The domain always goes from 0 to infinity, and the range goes from negative infinity to infinity. So let's take a look at a couple of graphs. We are going to be looking both at the exponential and at the logarithm. So the exponential is the one that we talked about in class, which is in red. So this one just kind of always looks like a curve this way. The logarithm is a mirror image of that one. So it's a curve, but this time it's going to go down this way. So it goes through the point 0, or 1, 0, sorry. The exponential went 0, 1, so that's their mirror image. And then it also goes through the point of the base. That's when your base is bigger than 1. If your base is less than 1, remember that the exponential flips and starts going down this way. So my logarithmic is also going to flip, and then now it's going to go up this way. Again, if you would like to see the graph of a logarithm or the graph of an exponential and look at some points, you can always look at the graph in your calculator. So if I have like the log of 5, I can graph that, and we can kind of see what it looks like. Ooh, that's not what it should look like. What is this? Oh, sorry. Yes, that's what it's going to look like, because we should have the log of x. That's what we should have. That's a function. The other one was just a constant number. Okay, this is kind of hard to see, but hopefully you can kind of tell that there is the curve that kind of goes through there. But so if you had other ones, you could also graph them as well. Let's go ahead and look at transformations just like before. Our transformations are the same exact ones that we had in previous chapters, and the same one that we had in the section of exponentials. Go ahead and look through the transformations, read through that on your own time, and make sure you understand how they work. Here, looking at the graph, we have to graph g of x equals 3 plus the log base 2 of x. So the first thing we would do is go ahead and graph the original, which is the log base 2 of x. You can do that by plugging in points. And then the plus 3 just moves everything 3 points up. Again, you could also graph that one in the calculator. We haven't talked about how to do base 2 in the calculator, because notice the one I graphed was log base 10 of x. but we'll look at how to change